Okay, so I think we'll start just as the last few people come in. Welcome everyone to another one of the Landscapes Live online seminars. Today it's my pleasure to introduce Duna, who will talk about her ongoing work in New Zealand. Before I hand over to her, I just want to remind a few people, for those of you who haven't attended one of these before, we do ask everybody please to keep your microphones off for the duration of the talk. The chat will be disabled for the talk and then will be reopened 5 minutes or so before Duna stops talking, and you're then invited to post any of the questions that you have. Myself, Michael and Rebecca will be moderating the chat and will be asking the questions for you. If you would rather ask your question verbally, please raise your hand and we'll get to you as well. Okay, just for everyone, just to let everybody know, we are recording this session so that we can post it then on our YouTube channel, which hopefully some of you have been able to access over recent months and indeed years, because again, this time isn't always great for everybody. But thank you very much for everyone for being here. We're really excited to have Duna with us today. And Duna, yes, when you're ready, the floor is yours. Thank you.
Yeah, great. Thanks, Lizzie. So yeah, thanks for joining everyone who's here, and thanks to the Landscape Live organizers for the invite and for the work that they do in the background to contribute to keeping this community building initiative running. I think it's great, and I've been really enjoying a lot of the talks. So before I start, I'd like to acknowledge my co-authors here who have contributed to the work that I'll present today and who have been a great group of people to work with, really. So this talk is going to be divided in two parts. And actually, the title that I gave you for the Landscapes Live talk, so the title of the overall talk, corresponds mostly to the contents of the first part, in which I'm going to be presenting some new beryllium-10 catchment-averaged denudation rates and its controls. And with that, we're going to be able to better assess the question of where, how, and how fast do the southern Alps of New Zealand erode. This is work that has been recently submitted to JGR Surface. And for those who were there for my ETU talk, apologies because this may sound a bit repetitive, but I hope that you do stay for the second part of the talk, which was actually the original question that initiated this project, including part one, and the reason that motivated us going to New Zealand in the first place. So in this second part of the talk, I'm going to be showing some beryllium-10 concentrations from landslides, and in situ carbon-14 and beryllium-10 from landslides and from fluvial sediment. And that data is working towards assessing whether we can quantify landslide frequency and landslide-derived sediment fluxes on timescales of centuries to tens of thousands of years. But in this case, this is still preliminary work. Yeah, so starting with the first part of the talk, the where, how, and how fast do the southern Alps of New Zealand erode. Here, I'm showing you the western southern Alps of New Zealand, which is the part that we are going to be focusing on. So this is the fastest extreme part and the wettest part of the range. Here you can very nicely see the trace of the alpine fault. So this is a Google Earth image with vertical acceleration. And you can also see here our here Mount Cook, which is the highest peak, which you will see later in a SWOT profile as well. So why is this question important? Well, many of you probably know that the southern Alps of New Zealand are one of the fastest uplifting orogen on Earth, and also one of the places from which we base a lot of what we know on the interaction among tectonics, climate, and erosion. But actually, on timescales of centuries to thousands of years, the rates, patterns, and controls of erosion are not so well constrained. So, for example, thermochronology data would suggest that the fastest exhumation is happening relatively close or at the alpine fault, while GPS observations over one transect, more or less in this position here, of observations of 10 years, is suggesting that at least during this interseismic 10 years of GPS observations, maximum rock uplift seems to be happening at the main drainage divide. And sediment provenance data seems to agree that there's non-uniform erosion across the range, but there's conflicting results on whether most erosion is happening at certain elevations or if it's happening at certain distances between the alpine fault and the main drainage divide. So to address the how fast part of this question, we collected fluvial sediment samples from the outlets of 20 catchments along the alpine fault. So we are then going to use this data in combination with other observations and available constraints to explore the controls of erosion on the range which can help us better understand the erosional processes, so to address then the where and the how part of this question. So I'm sure if you're here, probably you're familiar about with cosmogenic nuclides, but just in case you're not, I would like to provide a brief overview. So cosmogenic nuclides are nuclides that form in the atmosphere and in the top 2 meters of the bedrock due to the interaction of atoms with the incoming cosmic rays. And they are only produced within the top 2 meters of the bedrock because cosmic rays are attenuated very quickly as they penetrate through dense material. And they follow an exponential decay. So here, this graph here is showing you how the production of beryllium-10 decays with depth. But about 2 meters, we have almost no beryllium-10 production left. This concentration of cosmogenic nuclides on sediment or on rock increases with the time that they are exposed in these top 2 meters of the bedrock where they can be produced. And it decays, of course, also exponentially with depth because so does the production. So therefore, cosmogenic nuclides can be used to estimate bedrock exposure ages and also catchment-averaged denudation rates. And the principle for this is that if rocks are exhumed slowly to the surface, they have a lot of time passing through this production zone of the top 2 meters of the bedrock. And therefore, by the time they reach the surface, they have a high concentration of cosmogenic nuclides. Well, if they are exhuming quite fast, they pass through this production zone very quickly, and they arrive to the surface where they are eroded with a lower concentration. So overall, when we collect a bag of fluvial sediment at the outlet of a catchment, we assume that it contains a representative mix of erosion across the different parts of the catchment, so that we obtain a catchment average concentration that gives us a catchment average production. Because the accumulation zone is limited in space and depth, the timescale over which cosmogenic nuclide denudation rates are representative for, it's also limited. So it's proportional to the erosion rates themselves. So cosmogenic nuclides that are from faster areas are integrating over a much shorter timescale than from areas that are eroding much slower. So that will become relevant later. But finally, yeah, let's jump into the data. So here I'm showing you this map is assumed in DM of this square here that you can see, and we focus in these catchments on the western side of the range. In red is the Alpine Fault that I pointed to you earlier in the Google Earth image, and in pink is the Marlborough Fault system. So now I want to show you for context, because this is going to be important later, the current distribution of glaciers. So this is these hatch blue zones here. So the parts of the orogen that have done the highest relief, so this would correspond here, which is more or less the area of Mount Aoraki that I showed you earlier in the Google Earth image. These areas, they have still quite big glaciers that cover between 40 to 50% of their catchment area. However, for most of the parts of the range, as you can see, glaciers are quite small, and they are located in the very top part of the relief. So they cover on average about 5% of the catchment areas and less than 1% for more than half of them. Yeah, so now let's look at the rates. So here in blue is the catchments that had been previously sampled by Isaac Larsen and colleagues, and in black is our catchment. So the first thing I'd like you to notice is that we are quite happy that for those catchments that were also analyzed by Isaac Larsen and colleagues and by ourselves, so for example, here the Karangarua catchment or here the Wacharoa catchment, we find quite a nice reproducibility of the denudation rates, which is quite reassuring. Overall, we find beryllium-10 denudation rates between 0.6 to 9 millimeters a year, except for these 2 glaciated catchments that are located in the fastest exhuming zone, as I mentioned, where we found incredibly low beryllium-10 concentrations close to the blank levels. So as a result, the estimated denudation rates are very high, but the estimated uncertainties are also incredibly high. However, we think that in reality, it's very unlikely that these denudation rates are lower than 9 millimeters a year. So we think these should be treated basically as a minimum of 9 millimeters a year denudation rates. And overall, we just treat them as very rough estimates of incredibly fast erosion, but we don't include them in any of the regressions that I'll show you later. Yeah, for clarity. Because enhanced sediment fluxes after major alpine fault earthquakes, we know from turbidites in lakes, more or less the enhanced erosion post-earthquakes lasts for 50 to 60 years. And we know that the last earthquake in the Alpine Fault was in 1717, This means that our beryllium 10 denudation rates are mostly capturing interseismic erosion. So they won't even capture for most of the catchments, except for the very slowly eroding ones, any of the poles of sediment that could be associated with earthquake activity. Now, to start exploring the controls on these erosion rates, we also compiled 490 published zircon fission track, zircon helium apatite fission track, and apatite helium cooling ages. So it is challenging to convert these published cooling ages into reliable exhumation rates because the geometry at depth of the alpine fault ramp is not very well known. But we can make some first order estimates by assuming vertical exhumation pathways. So these serve to characterize the distribution of exhumation along the range, the order of magnitude. And we have done that with the recent H2 strip, but by Van der Beek and Chilgen. So this is the map of, so here I'm showing you first before the map, the point of each of the samples from which we estimate the exhumation rate. And this map is basically showing the interpolated exhumation rate. So you can see that this fastest exhumation, more or less in this area here, so where this highest relief area is of the glaciated catchment, and also we have secondary peakatron here. So now to start comparing rock uplift and erosion, I'm showing you here a swath profile of the elevations on the range, so that in the y-axis elevation and the distance along the alpine fault in the x-axis, and this is our Aki or Mount Cook in this peak here. So now I'm superimposing the alpine fault throw rate estimates that are based on the offset of late quaternary landforms. And you can see that throw rates are greatest here where relief is greatest, and they decay overall towards the southwest and towards the northeast. Now, using the same swath profile as background for reference, what I'm showing you now is the swath distribution, so the distribution of the swath profile, sorry, so the distribution of exhumation rates along the alpine fault. And you can see again that we see the maximum exhumation where relief is highest and where post throw rates is highest, and also an overall kind of taper distribution where exhumation rates decrease towards the southwest and towards the northeast. Now, what I have added here in blue is a swath profile of the current glacial extent. So you can see that the active glaciers are extending to lower elevations here for these two central catchments that I mentioned earlier. But for the rest of the range, glaciers are only located in the very top part of the relief, or they have completely disappeared. Now, superimposing our beryllium 10 erosion rates, you can see here, so again, ours are in black and Isaac Larsen's are in blue. And we can see that indeed the zone of extremely fast erosion, which probably is faster than more or less around here, is located in these two catchments that have the highest throw rate and exhumation and the most intense glacial coverage. And there's an overall decrease also in erosion rates, more or less towards the southwest and the northeast. But really, other than the order of magnitude, on the order of millimeters a year, in these very roughest order patterns, tectonics does not seem to be explaining very well our erosion rates. This is probably better visualized by these quite ugly graphs, where I'm comparing the beryllium 10 denudation rates here on the y-axis against the alpine fault throw rates here in the x-axis. And in this case, again, denudation rate in the y-axis against the catchment average exhumation rate calculated from the interpolated map that I've just shown you. So you can see here that there's still a lot of variability in the denudation rates that does not seem to be explained well by tectonics. However, we find a relatively good agreement of beryllium 10 erosion rates with KSM and with the erosion rates that could be derived from suspended sediment yields. So here you have denudation rates in the y-axis against mean catchment KSM, and here we have the suspended sediment yields in the y-axis against the beryllium 10 denudation rates. And as you can see, they fall quite close to the one-to-one line. So that was quite promising. It means that we were capturing the erosion on the range probably relatively well. So with this data, we started exploring the controls on denudation rate variability, and we checked for all the usual suspects, so differences in precipitation, in lithology, in slope, in the degree of glaciation, distance from the fault, because as we saw, there was some provenance work that was suggesting that the distance from the fault, there was certain distance from the fault where erosion was enhanced. But we found nothing remarkable. So I'm going to skip through those graphs, but if you are curious about a particular one, I have them in the hidden slides, so I'd be happy to show you later. So yeah, overall, we found nothing remarkable that seemed to explain well the variability of erosion of the range, except for elevation. So what I'm showing you here is a color map of the coefficient of determination, so the R-squared values that result from plotting the beryllium 10 denudation rates against the proportion of catchment area that falls within different elevation windows for different combinations of central window sizes here in the x-axis and bin window sizes here in the y-axis. So, okay, that sounded quite convoluted. What I mean by all of this is that we are looking for the optimized elevation window that best explains our data set. And we do that for different combinations of where this window falls at different elevations on the range, and also how big or small, how wide or narrow this window of elevations is. And we find that the proportion of catchment area within the 1500 to 2000 meter elevation explains more than 70% of the variability in denudation rate, as you can see here. So yeah, again, this can be better visualized if we plot this directly. So here in the y-axis, I'm showing you the catchment average denudation rate. And on the x-axis, the proportion of catchment area that falls within this 1500 to 2000 meter above sea level elevation. So we then explored what could be special about this elevation window, but found no evidence of a specific lithology or highest precipitation or increased slopes. And with the data that we have, we also don't find evidence of fastest uplift here. The only significant difference that we found is temperature, which, as you know, is highly dependent on elevation. So this elevation window, surprisingly, also coincides with the frost-cracking window that has been suggested by Hales and Goring based on their work between 2005 and 2009. So they found that there's a lot of frost-cracking scree at elevations just below 1500 to 2000 meters, and that this is the elevation range that hosts the most intense frost-cracking activity on the range. And in this case, for the Southern Alps, this corresponds to elevations that have median annual temperatures of between 0 to 4 degrees. And they found fewer scree on the western side of the range than on the eastern side of the range on their original paper. So they attributed that potentially to the fact that perhaps frost cracking was a less of an important process in the western side of the range compared to, for example, landsliding. However, with the data that we have now, and of course, aerial imagery has really improved, we see plenty of frost cracking derived scree at this elevation range. So we think, which is also another explanation that was suggested by Hales and Goring, that the differences in the map scree could actually reflect more differences in the preservation potential of the scree, giving the much wetter, the highest precipitation that we have on the western side of the range compared to the eastern side. This elevation is mostly composed of bare bedrock. So here I'm showing you the different distribution types of land cover for this elevation range. So you can see that it's like about 80% is bare bedrock, and we have at around 20% that is still composed by glaciers. And all other like scrub vegetation, it's basically negligible. This does not change much if we go back in time and try to infer what would have been the extent of glaciers and the extent of bare bedrock at those elevations at the beginning of the integration timescale of our denudation rates. So as you can see, these don't change much, and these do not change much either. However, I should also point out that we also compare directly the denudation range against the proportion of bare bedrock within the catchment, and we did not find that seemed to explain the denudation rates as well as elevation did. So it's not simply the bare bedrock that seems to be enhancing erosion. Here on the right, what I'm showing you is the distribution of the horizontal distance to the nearest glacier for all the areas within this 1500 to 2000 meter elevation window. So what you can see is that 50% of the pixels that are found at these elevations are within 300 horizontal meters from the nearest receding glacier, and 80% are within one horizontal kilometer of a receiving glacier. So basically, this elevation range is the zone from which glaciers have more recently receded. So it's the zone of paraglacial erosion, where permafrost thawing and glacial retreat and hill slope adjustment following this retreat could be enhancing erosion. So we think that enhanced erosion at this elevation is probably the result of the overlap of peri and paraglacial erosion. And indeed, from Hales and Goring work, they suggested that frost cracking activity could penetrate to depths of up to 2 meters within the bedrock. So this could be facilitating and conditioning mass wasting and enhancing the paraglacial landsliding. So unfortunately, there is only one small landslide inventory that spans above the tree line in the study area. So here I'm showing you the frequency of landslides for different elevations that they found. And this dashed line here is the pre-1950s rock falls, and this line here is the post-1950s rock falls. So they observed a shift towards greater elevations of the zones with more frequent landsliding, and they suggested that this could be due to permafrost degradation and hill slope adjustment following glacial retreat, so to paraglacial erosion. And for reference, this is where our elevations fall in, so in between these two peaks. However, unfortunately, this is only based on 500 landslides, which is not a lot, and has a relatively low temporal resolution. But this is promising. This enhanced erosion at these elevations would also be compatible with some of the sediment provenance data that has been done based on Raman spectroscopy of carbonaceous material. So this is work that is characterizing the peak metamorphic temperatures from which sediment comes from, and there's very nice metamorphic bands away from the alpine fold that can be used for tracking provenance. So here in this work by Zhao and colleagues, they found that since the beginning of the Holocene, more material has been coming from the chloride zone, which in their studied catchments corresponds to higher elevations. So they attributed this trend to paraglacial landsliding and response as glaciers are retreating. And actually, we now have more provenance data from the same samples that I showed you the beryllium-10 data from. And this is now being done based on circumfission track and also Raman spectroscopy by one of Carl Lang's PhD students, Ruan Harris at Georgia Tech. So if you're interested in this, stay tuned, because I hope that for AGU, there's new data to show for that. Now, I now forgot if I mentioned that these graphs, these very ugly graphs, still had some, there was still some hope for them. So yeah, indeed, they, as I said, don't look the best. But now I want to extract the residuals. So here, we're extracting the residuals from this linear regression. And in the next graph, what I'm going to do is to zoom in these two graphs so that you can see them better. So here, what I'm showing you this graph in the left is the residual of the regression between beryllium-10 denudation rate and the fall-through rates of the catchment outlet. And here in this graph, what I'm showing you here in the y-axis is the residual of the regression between denudation rates and the catchment average exhumation rates. And on the x-axis, in both cases, what you see is the proportion of catchment area within this peri and paraglacial erosion window. So as you can see, it seems that the proportion of catchment area at these elevations not only does seem to explain the denudation rates themselves, but also their departure from the rock uplift rates. So what we find is that catchments with less than 13% of their areas in the 1500 to 2000 meter elevation range have a lower denudation that would be expected given the rock uplift rate, while catchments with more than 13% of their areas in the elevation range, with more than 13% of the catchment area within this elevation range seems to have faster denudations that would correspond to the rock uplift. And this departure seems to be by a ±3 millimeter a year difference, which is pretty significant. So it would suggest that temperature control processes are modulating the tectonically controlled erosion by a significant degree. And they are probably operating at denudation rates of more than 2 millimeters a year, which would support the periglacial basalt hypothesis. If we consider the percentage of the total denudation that seems to be explained by this climate modulation, it's on the order of 40 to 80% of the denudation rate values. So this is pretty significant, we think. Moreover, you can see that the slope of these trends is very similar, and it could suggest an increase of 0.2 millimeters a year for every 1% increase in catchment area that falls within this peri and paraglacial erosional window. However, we should also, of course, point out that we think that this enhanced erosion with elevation is probably a transient feature. So, for example, we've seen the example of how landslide frequency seems to be shifting up. So most likely this zone of fast erosion will also be shifting up. But as it shifts up, it will encounter less and less surface area of the range at higher elevations. So that would probably result in an overall decrease in erosion rates. Now, are we claiming that we have managed to basically unpack climate and tectonics and isolate their effects? Well, not really, because of course we need to acknowledge that it's tectonics what push mountains to elevations within that elevation range where periglacial processes and paraglacial processes operate on the first place. So we think that the correlation between denudation rate and the proportion of catchment area at 1,500 to 2,000 meter elevation is so good because it's embedding tectonic information already on it. So this is perhaps better visualized if we look at this graph here, where in the y-axis I've plotted the proportion of catchment area with median annual temperatures of between 0 and 4 degrees, which for the Southern Alps is the temperatures that we find at these elevations. And here on the x-axis, I'm showing you the mean catchment KSN, which is a proxy for rock uplift. In our area, it correlates both with the fall throw rates and with the exhumation rates. So what we see is that as flow rates or rock uplift rates increase, so does the proportion of the catchment area that falls within these elevations where peri and paraglacial processes can be active. And as a result, erosion, the denudation rates and erosion rates increase. And this is seen here by this color mapping of the beryllium-10 denudation rates. What is remarkable is that we can characterize that temperature is an important modulator. Sorry, I'm not in my office and someone is phoning. Yeah, I'm visiting ETH doing some carbon-14 extraction, so sorry about that. Yeah. Yeah, so what is remarkable is that we can characterize that temperature is an important modulator in erosion rates, and we can characterize the rate at which it seems to be modulating tectonics, and that it seems to be correlating with denudation rates much better than rainfall is. So here, as an example, I'm showing you the beryllium-10 catchment average denudation rates against the catchment median annual precipitation, and you can see that it seems to precipitation seems to explain the denudation rates much worse than temperature does. And also the correlation catchment median annual precipitation and KSN, sorry, seems to be much worse. Okay, so basically the take-home message for all of this is that we think that in the Western Southern Alps, the links between tectonics and climate may be dominated by temperature rather than by rainfall-driven erosion. And this is an effect that we think that landscape evolution models are currently overlooking and that should be incorporated in them. Now, to start the transition to the second part of the talk, probably many of you are wondering how do our beryllium-10 erosion rates compare to landslide erosion rates? So here I'm showing you in the y-axis the landslide-derived catchment average erosion rate from the landslide inventory from Niels Hobbius and colleagues in '97. And this is plotted against the beryllium-10 catchment denudation rates. So as you can see in this case, the landslide erosion rates seem to be greater than our catchment average denudation rates. And that would not be compatible with, in principle, with our denudation rates, because this landslide inventory was derived for landslides just below the tree line. And we are arguing that most erosion seems to be happening above the tree line. However, one thing to keep in mind is that also this inventory is based on observations from a few decades. It actually represents long-term estimates of landslide erosion because it's extrapolating landslide erosion to kilo-year timescales based on the observed frequency magnitude relationships that I'm showing you here on the right. So in case you're not familiar with this type of graph, what it's doing is that it's reflecting the fact that the bigger landslides, so those with a greater area here, are less frequent than smaller landslides, which here have a much higher frequency. So in this case, maybe the longer term erosion rates below the tree line would be greater than our beryllium-10 erosion rates, because our beryllium-10 denudation rates may not be capturing the biggest events that are captured by this frequency area analysis. However, more recently, Robert Emerson and colleagues extended this same inventory here that has been used to derive long-term erosion rates, and they extended it to cover the period up to 2014. And in this case, what I'm showing you here, so they only report landslide volumes, and I've just divided their landslide volumes by the catchment area and their observation time span to estimate the catchment erosion rates. So in this case, you can see that our denudation rates are much greater than these volumetrically derived, actually decayed landslide erosion rates. This inventory also occurs mostly below the tree line, so it's basically an expansion of this other inventory. But there are three main differences between these inventories. One is that, yeah, it is based on the volumetrics, so on the actual landslides that have been observed and not extrapolating to longer terms. The other one is that to estimate volumes, they used a regional published area volume scaling relationship, unlike the older 97 inventory that at the time there was not this data available, so they used a linear relationship to correlate area and volume. And also when the time span of observation was increased, they found an overall lower frequency. I'll show you that later in another slide. So in this case, you can see that these landslide erosion rates would be compatible with our conclusion of enhanced erosion at above the tree line, essentially. For reference here, I'm also plotting the soil erosion rates from Isaac Larsen and colleagues, which they estimated based on 13 soil pits. 12 out of the 13 soil pits had erosion rates between 0.1 and 1 millimeter a year. There was only one data point that was about 2.5 millimeter a year that I'm not considering here. So what are we doing next before I move into part 2? Next, we are going to be recalculating the long-term landslide erosion rates based on the lower landslide frequencies that were found when the period of observation was extended. So this can be seen here. So these are landslide rates for different bins of time. And as you can see, since the 80s, which is not being captured by the older inventory, it seems that landslide frequency has decreased. So these longer term estimates may be also slightly overestimated because they just seem to have captured a period of enhanced frequency of landsliding. We are also then going to be comparing the area volume scaling relationships that were used with our field-derived, photogrammetry-derived landslide area volume scaling relationship. And with all of these, we are going to try to unmix the contribution of erosion rates from landslides and from soils. So that links up quite nicely with part 2, which was the question that originally sparked this project, which is whether we can, if we can quantify landslide frequency and landslide-derived sediment fluxes over timescales of centuries to tens of thousands of years. So why is this question important? Well, I guess if you are here, you already agree that landslides play a very important role in the evolution of relief and are a major source of sediment. They are also a major geohazard, and they are very sensitive to changes in climate and in tectonics. However, as we've just been seeing in this graph again here, bigger landslides that do most of the geomorphic work and deliver more sediment are relatively infrequent. So we would only observe the whole spectrum of landslide sizes if our observation timescale was on the order of thousands, tens of thousands of years, or even longer in some cases. But remote sensing data is only capturing landslide frequencies and landslide sizes over timescales of years or decades, while for bigger landslides, they can leave a physical evidence in the landscape, so they can leave scars and deposits, but that physical evidence is mostly removed in less than centuries or thousands of years. So if we manage to make the answer to this question yes, if it was a yes, we can quantify landslide frequency and landslide-derived sediment fluxes over longer timescales, I would argue that we could better constrain landscape evolution. We would be able to make better risk assessment, and potentially, if we were able to read paleo-landslide rates from sedimentary archives, we could be using those as markers for climate and tectonic changes and the impact on the Earth's surface. So the way that we decided to address this is using cosmogenic nuclides, but in this case, combining beryllium-10 and in-situ carbon-14. And the where was the Southern Alps of New Zealand and the Fiordland in comparison to each other. So the reason why we went to the southern island of New Zealand in the first place is because it has excellent landslide inventories. So these inventories show that landslides tend to be smaller, shallower, and less frequent in the Fiordland than in the Southern Alps. And in the Southern Alps, they are bigger, deeper, and more frequent. It's a good place to explore how different landslide regimes, in terms of frequency and sizes, are reflected in the cosmogenic nuclide concentrations. Moreover, in these regions, there is a quite unique data set from Clark and Burbank, who use freeway velocity surveys, seismic surveys, to characterize the gradient in bedrock fracturing with depth. So what they found is that bedrock fracturing decreases quite sharply with depth in the Fiordland, which limits the depth at which landslides can nucleate, and that's why landslides are generally shallower and smaller. Well, in the Southern Alps, because we are quite close to the Alpine fault and there's a lot of convergence, the bedrock is very pervasively fractured, which allows the generation of bigger and deeper landslides. And this can be seen in two published inventories that I'm showing you here, where these are based on remote sensing data in both cases. And as you can see, the overall frequency of landsliding. So this is given by this gap here between the pure land data here in black and the Southern Alps data. This is the same graph as I showed you earlier, but simply replotted. So we can see that they are shifted by an order of magnitude on the y-axis. That means that landslides in the Southern Alps are an order of magnitude more frequent. The size of the biggest landslide recorded is also an order of magnitude greater in the Southern Alps, and so is the size of the most frequent type of landslide, which is an order of magnitude greater for the Southern Alps than for the fjordland. So this is one of the few places in the world, if not the only place, where if we collect a bag of sand from a river, we can with some confidence say that the proportion of material that comes from landslide most likely come from smaller landslides in the fjordland and from bigger landslides in the Southern Alps. So just to show you for reference, I won't have time to dig into this data, but for this part of the project, we also have some beryllium-10 catchment-averaged denudation rates for the fjordland, which are between 0.15 and 1.45 millimeters a year. So they are confirming basically what we could see here, that overall erosion rates and landslide erosion rates are an order of magnitude lower in the fjordland than in the Southern Alps. But to start addressing this first part of the question on whether we can quantify long-term landslide frequency, we sampled 17 recent landslides, 4 in the fjordland and 13 in the Southern Alps, all of which have occurred within the last 20 years. And we wanted to sample recent landslides because we wanted to be able to neglect any post-landsliding accumulation of cosmogenic nuclides. So to clarify the sampling strategy, what we did was to walk up and down as many places as we could and were accessible throughout the landslide to collect an amalgamated sample that we considered representative of the bulk of the slip bedrock mass in a similar way to catchment. So basically, the concentration of cosmogenic nuclides within this landslide deposit is reflecting the concentration that the hill slope had integrated by the depth of the landslide before the landslide occurred. And for each of these landslides, we also collected drone footage to build DMs of the landslide scar. So from that, what we can then extract is basically a distribution of excavation depth within the landslide that we can use to calculate a bulk volumetrically weighted and depth integrated production. So if we divide the measured beryllium-10 concentrations from this landslide deposit by this bulk production rate of the slip bedrock mass, so what we obtain essentially is an exposure age of the hill slope before the landslide occurred. So this is shown here in the y-axis. And here, landslide area is calculated from the photogrammetry data, it's on the x-axis. So in this case, we've assumed no surface erosion before the landslide occurred. So this represents minimum exposure ages for now, and we'll be refining this later. So as you can see, we find exposure ages of between 1 to 16,000 kiloyears, so to 16,000 years. And we see that basically hill slopes that produce bigger landslides and hill slopes from the fjordland, so those are in red, had been accumulating beryllium-10 for longer before the landslide happened. So they have a much longer exposure age. Now, if we assume that in between landslides, the production profile of beryllium-10 is completely reset, which is an okay assumption for our case, because as we saw, the production of beryllium-10 decays to almost zero at 2 meters deep, and landslides in this area tend to be 2 meters deep or deeper. Then we can consider these exposure ages as a proxy for landslide recurrence intervals. So essentially, what our beryllium-10 exposure ages are recording is the time span that occurred between the landslide that we have just built and the previous landslide that had occurred on the same hill slope. So therefore, it makes sense that bigger landslides have longer recurrence periods, so have longer exposure, because we know that they are less frequent. So I should point out that as far as we are aware, this is the first data set of this type, because previous studies focused mostly on dating when landslides had happened, and we knew when landslides had happened, and it's by knowing that they were very recent and having a very good control on the depth that we could then use them to infer landslide recurrence intervals. And the reason why that's exciting is because it's relatively easy to convert landslide recurrence intervals into landslide frequency estimates. So they are basically the inverse, and then we have just scaled it up to kilometer square parcels. So then we can then compare them to the shorter term inventories. So here I'm showing you the same frequency area plot that I showed you earlier from the Southern Alps, so based on the Hobby's 97 paper. This time it's replotted in non-cumulative form, that's why it looks slightly different. And if we plot now the frequency that would be based on our beryllium-10 erosion rate, you can see that it, well, first plot with a very similar slope, which is nice and reassuring because this is slope of the decay in frequency with size. It's very important within landslide inventories. And we are getting reasonable landslide frequency estimates, which is also reassuring, given that this data is very heavily binned and represents observations from more than 7,000 landslides, and we have 17 landslides. So now we have two data sets of frequency area data, a short-term one based on the observation of aerial photos, and a long-term one based on the beryllium-10 data. And how long-term depends on its exposure age in particular of its hill slope, but on average it would be on the order of 2,000 to 4,000 years. Now, you probably noticed that there's an order of magnitude difference in the frequency. So this is something that we are going to be exploring in the future, whether this could be suggesting an increase in landslide frequency towards the present. We have also seen, however, that these frequencies could be slightly, not overestimated. It just happens that when this inventory was mapping these landslide frequencies during those decades were greater than when they are integrated over a longer observation timescale. So this could be bringing the model frequencies down slightly. Or it could also be related to a spatial gradient in landsliding, which we have also seen seems to be occurring on the range because most of our samples were collected at lower elevations closer to the Alpine fault. Now, for the Fiordland, we have way fewer data points because, of course, that's a consequence of landslide frequency being much smaller. It's harder to find landslides to sample there, but overall, they seem to be plotting also below the modern frequency lines. Now, before I finish, I'll try to be a bit quicker with this. I want to provide some more background on cosmogenic nuclides to address the question of whether we can quantify landslide-derived fluxes over longer timescales. So, cosmogenic nuclides, very simplified, they are produced through two cosmic ray particles mostly, muons and neutrons. Muons create spallation reactions, and muons and they decay much faster with depth, while muons can penetrate much deeper within the bedrock. So they interact less with matter, and the attenuation length is much longer. Now, beryllium-10, so muons only account for 2% of the total production of beryllium-10, and that's why here, if we look at the beryllium-10 production with depth in blue, and the production through spallation reactions in black, these lines plot almost exactly the same. And as we saw earlier, they seem to decay completely at 2 meters depth. However, for carbon-14, about 20% of the total production is due to muons, which means that carbon-14 production decays much more slowly with it. Also, this will be important for later. The half-life of carbon-14 is 3 orders of magnitude lower than that of beryllium-10, which means that when, for example, sediments are stored and buried, carbon-14 decays much quicker. So these differences in the production mechanisms between these two nuclides make the carbon-14 to beryllium-10 ratio very sensitive to depth. So this can be seen here in this figure that shows how the carbon-14 to beryllium-10 ratios decay with depth below the surface. You can also see in this graph, however, that this property also makes these carbon-14 to beryllium-10 ratios very sensitive to surface erosion because that affects how long the minerals spend at different depths. But overall, we can see that these ratios are very sensitive to depth and erosion rates. So they could potentially be used to fingerprint landslide-derived sediments. So, of course, this is going to depend on more aspects as we saw erosion rate. But for our purposes, for the last few slides of the talk, we should keep in mind that if a process that is only affecting surface erosion, so a surface erosion process, would deliver sediment that has carbon-14 to beryllium-10 ratios, or between 3 to 4, while those processes that are excavating deeper within the bedrock would deliver sediment that have carbon-14 to beryllium-10 ratios of between 3 and 4. Sorry, of more than 3 and 4. So to test this, whether this we observe in the landscapes, we measure also carbon-14 in 9 of our landslide samples. And here I'm plotting it against the mean landslide excavation depth from the photogrammetry. So you can see that indeed we find that landslides that excavate deeper in the bedrock are delivering material with higher carbon-14 to beryllium-10 ratios. So this could potentially be used to fingerprint landslide-derived sediment. So then, of course, the next question that we are currently exploring, and by currently I mean exactly at the moment, I have to load the sample after this talk is over. I'm currently at ETH doing this work, is that we also measure then carbon-14 on the pluvial samples, because we are interested to see whether this signal from landsliding is transmitted to the pluvial sediment. So what I'm plotting here is for the Fiordland in red and in black for the Southern Alps, the carbon-14 to beryllium 10 ratios of pluvial sediment for different catchment-averaged denudation. So this is very preliminary data, but for now we can see that most samples in the Fiordland seem to have ratios of below 3 that could be reflecting sediment burial and storage, which is consistent with the fact that they have very wide glacial valleys with a lot of sediment storage. While those samples from the Southern Alps have ratios that seem to only be able to explain either by extremely fast erosion or by landslide input. Of course, in detail, these ratios are affected by all these other variables that I'm showing you here. But luckily, we have a lot of data on all these different variables, landslide depth, surface erosion rates, and the proportion of sediment derived from landslides. So we are going to explore this in more detail. But it's promising that we find that for those catchments that are eroding at similar rates, the catchments from the Southern Alps do indeed seem to be reflecting sediment source from more or deeper landslides, while the sediment from the Fiordland seems to be reflecting that fewer sediment is sourced from shallower landslides, or there's just a lot more sediment storage. So we are going to be exploring that in the near future. And with that, I'd like to leave you with my take-home message and take questions. And yeah, sorry, this is taking a bit longer than I intended. So thanks for your attention.
Thank you very much, Duna, for a really, really interesting talk. So I'm glad to see that we've already got a few questions in the chat. So we'll start with Trevor Faulkner's. So thanks for an interesting talk, Duna. Question 1, in Scotland, there's uncertainty and debate about production rates for beryllium. How confident are you in the local production rates that you've used? Now, there's a couple of questions, so I'll just read the other ones out for this particular message.
Yeah.
So question 2 then related to that, how does denudation rate vary then with lithology for your study area? And then question 3 refers then to a paper, or he thinks that there's a paper that shows that denudation rates increase to the south in the New Zealand Alps. Do you agree with that finding? So sorry, quite a few questions there.
Yeah, no, don't worry, I'll get into it. Yeah, so how confident we are in the local production rates? There's actually a quite good recent paper by Aaron Putnam and colleagues calibrating local production rates. So the beryllium 10 production, I'm not particularly worried, or definitely not more worried than I would be in any other part of the world, really, for beryllium 10. And the good thing about beryllium 10 is that even if the production rates vary, we can continue to update this data, and the effect would be largely systematic. So I don't think that would really affect most of our findings. How does the denudation rate vary with lithology? So with catchment average denudation rates, we cannot explore the question in as much detail as if it was designed differently, but we did explore whether we found rates of denudation for catchments that were covered in a higher proportion by certain lithologies, and we found no evidence of that. One thing to keep in mind as well is that most of the terrain here is this shoreline terrain. So the lithology itself is not so different. It's a metamorphic grade that changes, but let's say the quartz content is not really different. It's all the same rock that has been simply heated up at different temperatures and at hotter temperatures closer to the fault and less away from the fault. The paper that he's mentioning, I don't think I know what paper they are referring to, because I've definitely not seen it. And in terms of denudation rates, as far as I'm aware, there was only Isaac Larsen's work on beryllium 10 in 2014. So I would love if you could please email me what paper you're referring to. Yeah. Should I move to the next question, Lizzie?
I can read out loud just for our
okay.
YouTube recording. So this is for Monica Rasmussen. Thanks you for the talk. And she said, frost weathering will be heavily dictated on the initial fracture geometry, poor connectivity, etc. Did you consider the impact of bedrock lithology fracture properties, spacing, as well as impact on permeability when investigating north versus south erosion rate disparity?
Yeah. So that's a really good question. So, I mean, first of all, I would like to say that our paper it's not about frost cracking. We just want to, basically we just find an elevation control, but we've mostly just characterized the beryllium denudation rates, and there's been a lot of other geomorphic work, and it's already a pretty massive paper. I definitely agree that the model that suggested frost cracking at between 1500 and 2000 meter elevation in this range is a simplified version that does not consider, for example, factor geometry or pore connectivity. I mean, those in a way, those are parameters that are incredibly hard to characterize at the landscape scale. And as far as I'm aware, there's not a lot of data. I think now there's efforts actually being done towards installing, for example, rock temperature probes and prognometers within the Southern Alps, but that data, as far as I'm aware, is not published yet. So there really isn't an availability of much better data that could allow us to update this model. So for now, we are using the model that is already published, which also, as I mentioned, has been validated by field observations of where frost cracking has been actually found on the range. So it seems to be doing a good job at capturing the overall patterns of frost cracking. Definitely, there's more details to be considered, but for our landscape scale purposes and longer term purposes, it seems to be doing a good job. But indeed, we would love it if someone updated the model to include all these details.
Thank you, Duna. Okay, so we have another question from Bobby Sass. And he says, have you looked into the influence of isostatic rebound from glacial retreat? How this affects fracture density / depth and the relationship with landslide nucleation?
No, we haven't. But I guess I would argue that in a way, the fault throw rates are all late quaternary. So they would be capturing those effects already on them. It's my feeling. But no, that's a good question. We haven't looked into that.
Cool.
Yeah.
So I think there's no other question in the chat. I have one quickly I can throw in a shine. I thought you go there, Lizzie, but I'm going to jump in first. So I was wondering, in that elevation zone where you see these peri and periglacial processes, what the river is doing? Is there any morphological change as it's going?
Yeah, that's a really good question. So I don't know if I go to, sorry, now you don't see my slides anymore, right? Or do you?
No.
Yeah, I don't know how I can show it. So basically, we found a very slight, okay, sorry, the display is disconnected. I apologize, this is not my office, so it's feel like issues, but I can just mention it. So basically, we looked into KSN, and it seems that KSN is slightly greater at those elevations, but with a 1 kilometer, considering a 1 kilometer square, for example, drainage accumulation, really only 1.3% of the drainage network falls within those elevation range. So we are basically at those elevations, we're basically just looking at hill slopes, not really channels. And in the few channels that do indeed fall at that elevation range are channel head. So it's not really representative. It's mostly the ridges that we are characterizing and the hill slopes themselves. So I actually do have a map of where this elevation falls. You see, you are not seeing, right?
I was running as well where the elevation of those head channels where they feed into the river downstream, whether they're in terms of depositing lots of sediment on the riverbed. And I don't know if that's an issue in.
Yeah, I mean, so now you're seeing my screen, right? Now we're seeing.
Yes.
Yeah, so this is what I intended to show earlier. So this is basically where this elevation window falls within the range. So as we can see, it's mostly either the main drainage divide, but here in this catchment, here it's a bit lower, or the interfluke divides in between the catchments or in between different subcatchments. And this is what I was mentioning, that we do find a slightly greater KSN at this elevation range, but this is how view of the drainage network falls in here. So, and then in terms of how the rivers look like, the truth is that it's really challenging to get samples from these areas. So we mostly focus for this work in the areas quite close to the Alpine fold, where you have these wide braided valleys, and we did not hike up the catchment so much because at the time most of the samples we wanted to collect, I mean, we needed to be close to the roads because we needed to collect a lot of rocks. So definitely looking into the catchments themselves is something for the future that I would love to do.
Cool. Thank you very much.
Okay, so I think we have a couple more minutes. If anybody would like to post some last minute questions, that would be great in the chat, or raise your hand if you would rather. I have a very quick question maybe to finish this up, unless anybody else wants to dive in. And I'm sorry, Duna, if I missed this initially, but could you just outline kind of the applicable or kind of average timescales for both your catchment wide erosion rates and your landslides? I'm just interested, like what timescales are we talking about, and how is that then, I guess, affecting how you're then looking at the landslide inventory?
So we have, so of course each catchment has a different integration timescale, but based on their particular erosion rate. The average is around 275 years, which puts the average after the major earthquake, the last major earthquake that happened in the Alpine Fault. But for this catchment here, are you seeing my arrow at least? Yeah, for this catchment here that I will be lower, this is the one that has the fastest, the slowest erosion, so the longest integration timescale, that's almost 1,000 years. While the ones here, the Fox and Whitefall, we only have an integration timescale from beryllium 10 of 60 years. So yes, of course, I mean, this is, pretty crazy. In terms of the landslide inventories, so there's landslides mapped at different time series since 1935 to 2014. So that would be the timescale of the observations themselves. Taking those frequencies, we could estimate the total landslide erosion to longer timescales. How much longer, though, it's not super clear, because basically it would be the timescale that it takes for whatever reference area you choose for the landslide. So it's on the order of thousands of years, we know, but I cannot give an exact number for now. We're going to be looking this into more detail. The landslides from the span above the tree line, honestly, it's just marked as a pre-1950 and post-1950. So it's hard to tell. And in terms of the landslides that we have sampled, again, we're getting a different exposure age for each landslide, but we are getting orders of, again, thousands of years. So we basically have orders of thousands of for each particular hill slopes, particular landslide, decades of remote sensing, and then the catchments are more on the order of centuries to 1,000.
Cool.
Yeah.
It's cool that you have quite a range then. That's quite interesting that you can kind of look at processes over those timescales. That's great. Okay. So there aren't any other additional questions, but thank you very, very much. That's been really, really great to hear what you're working on. Thank you again for putting together a really, really interesting talk. And thank you to the audience as well for your great questions and for coming today. Thank you very much.
Thank you very much, everyone.
Was really cool.
Yeah, thank you.
Thank you very much, Duna. That was really
there was someone, I'm just borrowing someone's office. He's
calling.
Yeah, I have no idea. No one ever calls me anymore again, to be, I don't know. Like, yeah.